Okay, can you see this slide? Let me put it full screen. So last time I had discussed about distortion-free systems, and we had seen some ideas about phase delay, group delay, other things. So today let me start with another part of the chapter. So here we are going to analyze what is the impact of poles and zeros on the frequency response of the system. So suppose I have uh, a pole close to the unit circle, what happens if I have a zero inside the unit circle or outside the unit circle? What do we like see the impact of that? So to understand that, we have to go back to what we had studied in the Z transforms. That is, we had studied that the Z transform system function or h of z can be represented as a ratio of two polynomials of z. So uh, for the for the case where you have a stable system, your system function will converge on the unit circle. That means the ROC will include the unit circle. So h of z can be written as h of e to the power j omega by putting the z complex number on the unit circle. So z equal to e to the power j omega. So if you replace that in the system transfer function, that is Vz by Az, where Vz order is less than Az, so M is less than M, and that is the idea for a proper rational function. So we have the zeros at Bk and the poles at Ak. So this is the expression for He of j omega. This is the frequency response written in terms of the ratio of two polynomials. Now these are like polynomials in terms of e to the power minus j omega. So so you can now split this in terms of factors. So you can write it like this, and there can be a constant term b naught which can come out, and then you will get a product of these uh, zeros and product of these poles. So zeros are at zk and poles are at pk. So we get this simplified expression where if we replace z equal to e to the power j omega, we get like this. So this is one way to write He of j omega in terms of ratio of two polynomials. And now we have factored the polynomials. So, so we can now start to think about how to write the magnitude, phase, and group delay when we are given the above expression. So then we can see the impact of each zero and pole on the phase delay and the group delay. Okay. So what we do is we take out the magnitude of the left hand side. That is, we take out the magnitude of this guy. So this will be written like this: the ratio of the magnitudes of the individual factors, and the angle can also be calculated. So you will have the angle of this constant term b0, and you have uh, like this summations will come because you are calculating the angle. So individually for each of the terms, you will calculate angle. Each of these are like complex numbers. So you will take the tan inverse of the imaginary part divided by the real part. So you will get the phase angle for each of these factors. So you will have various zeros and various poles. For each of the factors containing zeros and poles, you can calculate the uh, absolute value and the phase angle. And similarly, you can take out the group delay also. It will derive with respect to omega. So now these derivatives are calculated with the continuous or unwrapped phase response function. So I had told you that the wrapped phase response function, that is was between minus pi to plus pi. So if you find the phase response over more than minus pi to plus pi, that is, it can extend to minus n pi and to plus n pi, then you will get uh, discontinuities of 2n pi at each n pi. Okay, so at minus 2 pi, you will have a discontinuity of minus 2 into pi, and at plus 2 pi, you will have a discontinuity of plus 2 into pi. So if you discard those discontinuities, you will get a smooth function, which is the unwrapped phase response function. So these first order terms can be expressed in polar notation like this, because zk is a complex number. So you can write uh, zk into e to the power j omega minus j omega is alpha into e to the power j beta. So then pk can be written as like that. So if you generalize and think that zk and pk can be complex, then you can write it like this. So slowly we are coming to the expression where for each zero and each pole, you will see what is its contribution to the magnitude response, to the phase angle, and to the group delay of the system. So the LTI system is composed of many zeros and poles, and you can write the system function or h of z in terms of a ratio of polynomials in z inverse. Now that means polynomials in e to the power minus j omega form. If the h of z is and the ROC includes the unit circle. And then you have factorized the polynomials into the zeros and poles, and you are now looking at the contribution of each zero and pole to the magnitude response, phase response, and group delay. So slowly we are moving towards that expression. Okay, fine.
Yes, sir.
Shall I go ahead?
Yes, sir.
So now we have written the factor c of omega is 1 minus alpha e to the power j beta e to the power minus j omega. So this can be like written as cos of beta plus j sine beta, and this is cos of omega minus j sine omega. So then you can get the product terms here, which can be expanded and written like this. And c omega mod square, that is equal to c omega into c star omega or conjugate omega, that gives you, so c star or c conjugate omega is alpha e to the power minus j beta e to the power plus j omega, because you are taking conjugate. So if you multiply, you get this expression. So you can now find out the angle, that is phase response, and the group delay. So the group delay is calculated from uh, the phase response only.
Sir, in this case, we have to differentiate this angle of C of omega. To
Yeah,
get,
yeah.
okay.
That is a phase response, huh?
Oh, yeah.
And that is considered to be unwrapped phase response. Okay, can I move?
Yes, sir.
So if you write the zeros and poles in polar notation, assuming they are complex, that is the general case, then you can get these expressions. H, this is the magnetic response, and this is the angle. So what are you doing here? You just look at this expression. You are taking the square root of this scale. So if you see the previous expression 1 minus zk e to the power minus 3 omega, this is mod. So you have now written C of omega as 1 minus alpha e to the power j beta e minus j omega. That you have derived and like this. This is C omega mod square. So you take the square root of that, you will get mod of each zero factor and the pole factor. Okay, is it clear? You see this? I will take the square root of this because this is C omega mod square, isn't it? So qk into e to the power j theta k is the notation for z, the 0, and rk into e to the power j phi k is the notation for pk. So in the previous expression, here you just have to put, instead of alpha, you have to put q, and instead of beta, you have to put theta k. Theta. Okay. So similarly, you can calculate the angle by using these terms. So slowly we are seeing that what is the impact of the zero and the pole on the magnitude and the phase. Individual pole and individual zero. Okay. You can check with the previous expressions that you are putting these terms qk, theta k here, and you are putting rk and phi k in the poles. So can I move?
Yes, sir.
So the group dealer similarly can be written out like this. So these relationships are showing the influence of each individual pole or zero on the magnitude, phase, and group delay responses of the system. Okay, so we are done. Shall I move ahead?
Yes, sir.
Yes, sir.
So some comments about this dependence of frequency response on the poles and zeros. So the shape of the frequency response is determined by the impulse response or the coefficients of the difference equation. So the coefficient of the difference equation, you will have AK and BKs. So those are our locations of poles and zeros. So we cannot guess the shape of h of e power j omega mod and angle h of e power j omega by just looking at h of an or ak and bk. Yeah. So we have to write the expression like this, the previous expressions, then only we can think about what each pole and zero is doing to the impulse response, sorry, to the magnitude response, and the phase response, and the group delay. So just by knowing h of n or the difference equation, we cannot understand the shape of the phase response and the magnitude response. So we will show that there is a strong dependence of the shape of the frequency response on the location of poles and zeros of the system, and you can use this dependence to obtain a procedure for quickly determining the magnitude and phase response and to understand the action of different filters. That is, we can start to design filters by placing poles and zeros ourselves. So we can choose a particular location of the pole and the zeros, and we can choose how many poles and zeros should be there in the system function, and we can try to tailor or try to design the frequency response magnitude and the phase response to our liking. So there are various kinds of filters that we can make. We can make a notch filter, which will remove one particular frequency. We can create a comb filter, which will remove a set of frequencies from the magnitude response. So we can design those things. We can vary the gain of the filter to the way we want. Okay, so that we can achieve a certain kind of output. So which frequency should be allowed more, which frequency should be attenuated more, all that we can decide ourselves and we can design the filters. So this is the insight into filter design. So let me just begin with little bit today. So, so we have now seen that this particular expression can be written like this, and it can also be written like this. You see here, we have just tried to simplify this a little bit, and because of this simplification, e to the power j omega n minus m has come out. So we have just tried to simplify each of these terms a little bit. That is, we have taken e to the power j omega here, and we have tried to write it in terms of positive powers of e to the power j omega, and that causes this extra thing to happen here. So B naught is a constant, and these are zeros of the order n minus 1. We have m zeros, we have n poles. Okay, just a little modification. Done. So now you see this equation, the last term contains factors of this form. And this particular factor, e to the power j omega minus zk or e to the power j omega minus pk, can now be thought in terms of geometry. So you can think how this factor will look like on the unit circle, how inside the unit circle, how it comes like. The factor e to the power j omega minus zk is a complex number because zk is a 0 and e to the power j omega is sitting on the unit circle. So this particular factor is a complex number represented by a vector zk to z. Now here capital Zk to capital Z. This is vector notation, and on the top there is an arrow. So there is a vector from capital Zk to capital Z, where capital Zk is the location of the 0 and capital Z is on the unit circle. So you see here in the diagram, so this is the complex Z plane, and here you have Z, and Zk is here. This is the location of the 0. So this is a vector Zk to Z, this particular vector, drawn from the point Zk, which is a 0, to the point Z equal to e to the power j omega. This angle is omega. So this is e to the power j omega. On the unit circle, Z equal to 1 into e to the power j omega. So Z is here. Okay. So this is the way we can describe it geometrically. So we had said that our 0 will be located Zk. So Zk is written in terms of complex polar notation, and it has an angle of theta k. So let us see what was Zk. You see here, Zk is equal to Qk into e to the power j theta k. Huh. So the length is Qk, this length is Qk, and angle is theta k. Similarly, the pole, it was the pole pk, it was something like, what was that? Rk into e to the power j phi k. So the length was, suppose if this is the pole, then the length was Rk into e to the power j phi k. So there is a complex 0 here and a complex pole here. So this is our notation. And this particular factor is the vector connecting Zk to Z. Similarly, this particular factor is a vector connecting Pk to Z. And the vector containing O to Z has an angle of omega. And this vector has a magnitude 1. So Z is sitting on the unit circle. So slowly we are looking at the geometry of the individual terms. So these things will like slowly lead to new understanding of how to design filters. So where should I place my zero? Where should I place my pole so that I get a certain type of magnitude response and a certain type of phase response? Okay? So I can control the filter behavior by placing zeros and poles of my choice. Okay, are you able to understand what I'm saying?
Yes, sir.
Okay. So those who want to draw this diagram, they can draw. So if you see, you can find out the length of this particular vector by using the parallelogram law or the triangle um, like inequalities. So you can see that this is one, and this is zk has a what is that rk, right? That was rk or what was it? Or okay, qk. So qk into e to the power j theta k. So this length was qk. This is 1. So this guy will be 1 minus qk. Is it not? If you add 1 minus qk, you will get 1. So by vector addition, you can find out what is this length, zk z. So this term, you can find out what is the length. Similarly, you can find out this guy, qk to z, which corresponds to this particular term. So I think you have drawn this diagram, everyone.
Yes, sir.
Yes, sir.
This diagram is going to be very useful. That's why I'm asking and waiting so that you can all become comfortable with this diagram. If you have a doubt, you can ask me. Look at all the angles and look at the expression of the zk and uh, pk in the complex notation. Okay, fine. Let's go ahead one more. So e power j omega minus zk is equal to zk z vector, that is qk into e to the power j theta k. So qk is the distance from 0 zk to the point e to the power j omega, and theta k is the angle of the vector zkz with the horizontal positive real axis. So you see here, qk is the distance from here to here, zk to z. 0 zk to the point e to the power j omega, and capital theta k. So there is a small notation difference. You see, this is capital qk and this is capital theta k. So earlier you had small theta k here, and here you have capital theta k. Can you see this clearly? This is small theta k, this is capital theta k. This length of the zero is small qk. So this vector length is capital qk. Okay. So this vector can be written as capital QK e to the power j capital theta k. Whereas this vector is written as small qk into e to the power j small theta k. Okay. So similarly, this particular factor, this was for the 0, and then for the pole, we have a complex number which can be represented as pk to z equal to rk into e to the power j phi k, where rk is the distance from the pole pk to the point e to the power j omega. So let us see that pk to the pole, from the pole pk to the point e to the power j omega. This is the distance. This is capital Rk, but from here to here it is small rk. So small rk e to the power j phi k is the vector here. This particular vector is capital Rk e to the power j capital phi k. Phi k is this angle. I think all of you are able to see my cursor.
Yes.
This is capital phi k. This is small phi k. This vector length is capital Rk. This vector length is small rk. Okay. So now we can see that to replace, then the notation becomes very simple. It is just capital Qk of omega divided by capital Rk of omega, because the lengths are given like this. So capital Qk of omega, that means function of omega, but with Qk as the length of the vector. This entire thing is this vector. So you can get product of these vectors and again product of these vectors. And then you have the full term here. So the angle capital theta k and the capital phi k, they come in the phase response. So this expression is a nice expression by which you are able to simplify that complex factors. And you have now understood it in terms of vectors and angles. So this was a nice thing that I wanted to talk today about. Somehow the internet is not working in the institute. So now I'm accessing everything through my phone. Even to connect to the Google meeting, I had to copy paste, or I had to actually write down the Google meeting code inside the browser. So I don't know what happened today. There's no internet. So this is a nice expression that you have arrived at, where you are using the lengths of the vectors and the angles of those vectors corresponding to each of the factors. So each of the factors of zeros and poles are actually vectors. So I'll stop here because I'm exceeding the time. So I hope you have all understood up to this. Yeah, you understood, na?
Yes. So the reference book is track is sir.
The Process is there. Now I am teaching from another book. Okay, Process also has this, and OpenIM also has this. But now I am teaching from another book, that is Process and Ingley. Okay, that is another book written by Process. So this material is still there in Process Manalakis also, okay, which I have described. So that also you can see.
Yes.
So I am following some 6 or 7 books for this course. Many books. Whatever books I can lay my hands on, I am following from there. And whatever is simplest in any book, I am trying to give you. Okay. Because DSP is a complicated subject for the beginner. For the second time or the third time guy, it is easy. For the MTech guys, it might be easier. But for the UG guys, it will be a bummer. All the things like they will be bouncing over your head. So you have to be given very slowly all this material. And It has to be given in a very simplified form so that you understand. There are multiple books on DSP and very good books, but I cannot teach like every book, so I cannot make every book a reference book. Wherever I find good material, I take from that book. Okay, you can refer to process analysis. It has this, and Oppenheim has in detail all this. But Oppenheim like has lot of detail, and this particular chapter is written in a very hodgepodge way in Oppenheim. So it is a very daunting thing for a beginner to read Oppenheim. But for MTechs, you can refer to Oppenheim. This chapter is tricky.
Yes,
So,
thank you.
Proacus would be a better book for this than Oppenheim.
Proacus is a better book definitely for this chapter because notation is simple and it is all there in Proacus. You can refer to Proacus.
Okay, sir.
Don't get worried. I'm giving you very slowly the things that you're supposed to know. If you are making notes, sitting and making notes, you will understand everything. There is no doubt about it. Every equation I am clearing. Okay, fine. I'll stop today here. Thank you.